Good morning, afternoon or evening, as the case may be. I'm Professor Derry, and I'm going to give a little talk to you about the reporting of experimental errors in research, in reports of research, papers about research, and so on. The first thing to be quite emphatic about is that these experimental errors are not your mistakes. They are the accuracy of your measurements. No measurement is perfectly accurate, and this is something that you have to tell people about. And it's often not properly done, even by professors writing papers. This is not a proper statistics course. You can find the statistics of error analysis in many textbooks. This is just some practical examples just to show you where you need to use these things, because I think a lot of people know the theory, but they're not quite sure what to do with it. Here's a real example of some measurements of the quantity big G. Now, this is not little g, the acceleration due to gravity. This is the constant in Newton's law of gravitation. F is equal to m1 m2 over r squared. And these are some measurements that have been made by various people over the last 40 years. The oldest one's at the top, the most recent is at the bottom. And notice that these numbers actually don't differ by very much. They're all about 6.67 something, but you need to know this quantity terribly accurately if you're going to launch spacecraft, because you've got to do the calculations. The first thing to notice is that different labs, and these were well-known labs, have got values that differ by quite a significant amount. They are the blue dots. The red dots are the ones that were recommended values by the CODATA database. The other thing that's interesting is that these groups all reported their error bars. These horizontal lines represent the spread of the errors that they expected to have, and we'll see that they don't even overlap in many cases. And so the people who thought they knew what their experimental error was hadn't actually determined it very well, or they'd been terribly optimistic and quoted very small errors, whereas in fact they probably had quite big errors. So here are two very basic rules. Rule one, firstly, you must do error estimates. You must have some idea of the accuracy of your results and report that value. As I said, scientific errors are not your mistakes. They're the accuracy of your measurements, and the true value is unknown. You can't look it up in a textbook because there isn't a textbook. These are new measurements, presumably, if you're doing research. Nobody's ever done them before, and so it's up to you to give an idea of how reliable the value is. And rule two is use common sense when in doubt. You must have some sort of error estimate, and if you're not sure what to do, then use some common sense and don't quote things that obviously aren't right. And here's a good example, and you see this all the time, all over the place. A statement in a journalistic report, for example, the smoke from the burning factory billowed 305 meters into the sky. Really? Did somebody get up a ladder and measure it? It's a pretty long ladder. Clearly, this is not an exact measurement, and in fact, this very often occurs because they've translated a rough measurement. From imperial, 1,000 feet is exactly 305 meters, but this was a rough guess. Somebody was watching the fire and said, oh gosh, that smoke's going 1,000 feet, maybe 2,000. Let's quote it as 1,000. and then somebody converting it into metric converted it into far too accurate a number. And we say that it's got too many significant figures. Here's another slide showing the importance of significant figures. The Queen that's just died was crowned in 1952, and on the morning of her coronation it was announced that Mount Everest had just been climbed for the first time by a Brit. Actually, he was a New Zealander, but anyway, the Brits were very proud and announced that on the morning of her coronation, and they'd measured the height of Everest very accurately beforehand. They'd measured it to an accuracy of plus or minus 2 feet. And just in passing, that symbol plus or minus doesn't mean approximately, as some people think. It means that it was either anything up to 2 feet more or 2 feet less than the value that they're quoting. And the value that they got was 29,000 feet exactly. Now, they were a bit worried about that because it looks rough. It's good to 5 significant figures. All those zeros are significant figures because of the exactness of the measurement. But it looks rough. It looks as though it was just a sort of a guess to 2 significant figures. And they wanted to get around that, and the solution they thought of was just to add the error to that number and quote it as 29,002 feet. And of course, that's okay because the error is 2 feet, so it could be 29,002 feet, or it could be a bit less, but it's within the correct number. And when I was at school, that's what we always learned. The height of Everest was 29,002 feet. I'm not sure what the present value is. So another thing that we see from this is that you must quote significant figures that match the error. And here's another example of supposing the quantity that we wanted to announce in our results is 76824, and we calculate an error of plus or minus 135. Now, that means that those figures, the 2, 4, are nonsense. They're not significant. It could be just about anything else. The 8 is the last of the figures that we know well. In other words, it's the last of the significant figures. And so we should quote that answer 76800, round it off. And we should do the same with the error, because there's no point in quoting an error to 3 significant figures when it might be a fairly rough determination. And so quoting it to plus or minus 100 is what we should do. Maybe 140 if it was some sort of accurate statistical analysis, but I was always taught that errors are usually only good to 1 significant figure, and so think about quoting just to 1 significant figure. Beware of calculators or computers giving you huge numbers of significant figures, and they do. You've seen it. A calculator very often gives you an answer to 8 significant figures, and clearly most of those are nonsense. They aren't real, and you should round that number off according to the accuracy, according to the error that you've determined. If you're reporting a quantity that you got by adding some other quantities, how do you allow for the error? How do you combine the errors in those quantities that you've added up? Well, of course, you can add the errors. That's better than nothing. But in fact, the statistically proper thing to do is to add the squares of the errors. So if your answer is x plus y plus z, and delta x, delta y, and delta z are the errors in those quantities, then you add the squares of those quantities, delta x, delta y, and delta z, and take the square root, and that gives you the error in the quantity A, according to statistical theory, which you can go into in books. We don't have to go into it right now. We say that the errors are combined in quadrature. This is the proper way to do it. And if you're really stuck, and remember you must quote an error because other people are going to depend on your answers and the errors in your answers, then quote the answer to the least accurate decimal place in any of those quantities. And that will be the thing that affects the error of your final answer the most. If you get your answer by multiplying quantities together, as you often do, then the procedure is the following. Here is an answer B, which is x times y times z plus maybe a whole lot of other things. Then you must sum the squares of the relative errors. So delta x divided by x squared, delta y divided by y squared, and so on, and take the square root. And of course, that is going to give you a relative error in the quantity b. It'll give you delta b over b. If any quantity is raised to the power n, its error must be included n times. And it doesn't matter whether you are multiplying or dividing, you add the errors in every case, or add the squares of the errors. A rough method here, if you are really desperate, quote the answer to the least number of significant figures in any of the quantities that you've used to multiply by, because the ones with a lot of significant figures are probably quite accurate. The ones with the least number of significant figures are probably the least accurate. We note in passing that one error may dominate. That's quite common. One of the errors may be much bigger than the others. And if that's the case, you can neglect the others. You can include them if you want, but they won't make any difference to the answer, or so little difference that you will hardly notice it. Just to be specific, here's an example that you probably remember from first year, Poiseuille's equation for the flow of liquid through tubes. And here the equation is, it's got a lot of quantities in it. They're all multiplied or divided, and you find the relative error by taking the relative errors of the quantities eta and p and l and r and squaring them, and the radius comes into the fourth power. So we've got to add 4 times that relative error in our square root. And once again, notice it doesn't matter whether the quantities were multiplied in the original equation or divided. You always add the errors. It's an illustration of the fact that the errors never get smaller, they always get bigger if we include several of them. And notice that we've got a relative error in this thing Q, which is the flow rate through the tube. And if you want the actual value, the absolute value of Q, of delta Q, then we cross multiply by Q in order to get it. We can use either fractional errors, as I've done here, or we can use percentage errors, because percentages are, of course, a fraction. And so sometimes it's more convenient if you've got errors in percentages to use those. What to do if you've got funny functions in your calculations? Well, there are methods, and you'll find them in statistical textbooks, methods for combining sines, logarithms, and other funny functions. And you may have to look them up if you need them. But a rough and quick way, and quite a reasonable way, is just calculate your worst value using your most extreme numbers. Use perhaps your biggest values in the numerator and use your smallest values in the denominator, so that you'll get the most extreme result of your calculation and subtract the mean to get an error estimate. You'll get a very big one, but it's better than nothing. You must have some sort of error estimate. People need it because they want to use your results. It's hard to believe that sometimes, but some of the research that you do, let's hope all of the research that you do is going to be looked at by other people who are going to say, hey, this is great. I'm going to use this method in my research. And in order to do so, they need to know your errors. 2 things that we often talk about are precision and accuracy, and they're not the same thing. The precision is how exact your measurement is. For example, how many significant figures you were able to quote it for. But you can measure nonsense results to a very high precision. And here's an example of showing shots on a target, and we see that they're all in pretty much the same place, so they represent something that was quite exact, but they're in the wrong place, so they are not very good. Your accuracy is how good your measurements are, and another way of saying that is that they have low errors. So here is a target with some shots that are all on the bullseye, and so that is an accurate measurement. Now, there are two kinds of errors that we also talk about, random and systematic errors. And random errors are all over the place. They're due to the measurements. Sometimes the measurements are too high, sometimes too low. Maybe whatever machine you were using for doing the measurement doesn't give a very good one. Random errors show up in repeat measurements, and they're sometimes positive, sometimes negative, and they can be averaged out. Systematic errors are errors due to the equipment or the experiment, and they're always the same in repeat measurements because they're due to something that isn't quite right and that we haven't changed. They're much more difficult to get rid of, and they're much more difficult to find. You can spend a lot of time designing an experiment and trying to get rid of possible systematic errors in some place. Here's an illustration showing that with shots on a target again. In this case, these shots are all in pretty much the same place, but it's the wrong place. These measurements have got a systematic error, and we don't know what it is. Maybe the gun sight isn't very good, or maybe the guy who's doing the shooting isn't very good, but the error comes out the same in each case. Here is a random error. The shots are all over the place. They're also not very good, but they're not very good in different ways. Some are up, down, sideways, and so if you take an average, you will get a much better value. And once again, notice that the true value is unknown. We can't compare it with a textbook to check it. There is no textbook. Random errors are often assumed to follow a Gaussian distribution, sometimes known as a bell curve. And I say assumed in big letters because experimentalists often say, well, we know from theory that they'll be Gaussian, and theoreticians say, well, we know from experiments that errors will be Gaussian. So we have to be a bit careful about that. Often the distribution of errors that people have is not really Gaussian, but they say, oh, well, let's use a Gaussian because it's a known function and it's easy to manipulate mathematically. Here is the function, and I've written it out in full because it isn't always written out in full. It's an exponential function of a negative square, and x is a measurement and x naught is the mean of the measurements, and sigma is a quantity called the standard deviation, which is related to the width of the curve, and in front there's a constant, and often it's just written as a constant, but it actually consists of a combination of other things. There's a sigma in it, for example, and it is the n naught is the value of the probability at the mean. N is a probability. Big N is a probability of having a value of a certain size according to how far away from the mean we are. And we can also do a plot versus the errors, delta x. We'll get a curve which looks rather similar. If we use a little n for our actual measurements, then the mean, as you know very well, is the sum of the measurements divided by n. And it's the best value that we have. We can use the mean as the best value and the value that we present in our write-up or whatever it is. The quantity standard deviation related to the width of the curve does a similar sort of thing, adding up the squares of the errors and dividing by the number of measurements and taking the square root. And statistically, it's the likely error in an individual measurement. Now, quite often we aren't that concerned with errors in individual measurements, although people who have very few measurements, like the people who work at SAN, people working on the Higgs boson and so on, they've got so few measurements that they have to look very carefully at the standard deviation of their measurements to see whether they're good ones or bad ones. But we are much more likely to use the mean, and we want an error for it. The standard error in the mean is the standard deviation divided by the square root of n minus 1. The 1 comes from statistical theory. And just in passing, we notice here that now supposing we do 10 measurements. Well, the value of n minus 1 is 9 and the square root is 3. And so the standard error in our mean has gone down by a factor of 3, not 10. If we want to get the error down by a factor of 10, then we have to do 100 measurements. And so in order to get an accurate value by taking lots of measurements, we have to take a very large number. It'll be a better tactic to try and do better measurements. Here's a demonstration that helps us to understand whether a Gaussian distribution is theoretical or experimental. And if I was giving this talk live, I would do the demonstration. I've got a demonstration apparatus in the physics department here at WITS. It's called Galton's quincunx, and quin means 5 in Latin, and it's like a pinball board. These dots represent pins. The board's shown 3 times here. And they are arranged in 5s like the faces of a die, the 5 on dice. And so we have a funnel here full of little balls, and we pour them through, and they start hitting the pins, and some of them go left and some of them go right. And when the whole thing's finished, we've got a pile here in vertical columns, in tubes, in the apparatus. And the shape is very much the same as the shape of a Gaussian function. So what is causing that? It's because the resulting distribution is a result of lots of little errors, we can say, either positive or negative to one side or the other, and they will add up. Sometimes we will get 2 positive ones together, and sometimes a positive and a negative. And the result from all these little random changes is a function which is like this, and this is the mathematical function. So the theory says that a Gaussian distribution results from a lot of little random changes. Experimentally, we'll get a Gaussian if our experiment, or our measurements of the experiment, have a lot of little random errors in them, which are sometimes one way and sometimes the other. And we can think about that in order to decide whether the distribution that we should get is going to be Gaussian. As I say, a lot of people don't look at that. They say, well, let's use a Gaussian function, and sometimes the measurements that they make do not have a Gaussian distribution at all. So that's the final thing that you can think about if you want to analyze your results with the Gaussian distribution.